PPT,
Yes, sir.
and my audio is clear, na?
Yes, sir.
Okay. Okay, this is what we have discussed, Reynolds analogy. And Reynolds analogy says that friction factor divided by 2 equals to Stanton number for heat transfer equals to Stanton number for mass transfer. This is valid for gases only, and all the properties are estimated at average temperature. And then we have discussed Chilton-Colburn analogy. So this is the Chilton-Colburn analogy. So F by 2 equals to Stanton number for heat transfer into Prandtl number raised to 2 by 3. Friction factor divided by 2 equals to Stanton number for mass transfer into Schmidt number raised to 2 by 3. F by 2 equals to JH equals to JM for flow over flat plate. JH equals to JM for flow over cylinder. For sphere, JH equals to JM, and these are the limitations of Nusselt number. Flow through pipe, F by 2 equals to JH equals to JM, and this is the Reynolds number limitation for flow through pipe. And this limitation, again, all the properties are estimated at average temperature, and Prandtl number between 6.6 to 60 and Schmidt number between 0.6 to 3000. This is what Chilton-Colburn analogy we have discussed. And then we have solved this problem where you can see data from heat transfer is given. So in detail, all the data are transferring given. So you can do easily calculation because velocity is given, heat transfer coefficient can be calculated. So surface temperature and bulk temperature is given actually. This is surface temperature and bulk temperature. Surface temperature is not given. So if surface temperature is given, so this can be done. But what we have done using Chilton-Colburn analogy, we have done in mass transfer, calculation in mass transfer. So this Chilton-Colburn analogy we got. So here using this F by 2 equals to JH equals to JM. Colburn factor for heat transfer equals to Colburn factor for mass transfer. So this is rearranging this equation. So this JH equals to JM. So Stanton number into Prandtl number raised to 2 by Schmidt number. So rearranging this equation, so we got this, and we can calculate the mass transfer coefficient. Once mass transfer coefficient is calculated, I can calculate the rate of mass transfer. Similarly, using JH equals to JM, I can F by 2 equals to JH. So using this, I can calculate friction factor. Then using Finding equation, I can calculate the momentum flux at the wall. Using that, I can calculate the drag force exerted by flowing fluid on the wall. So importance of the analogy. So analogies are used when a detailed data is given in one area. Heat transfer coefficient is given, so I can estimate mass transfer coefficient and friction factor. That is what the use of analogy. But you need to remember the limitations of analogy. And as I told, there can be many analogies available. Okay, many analogies are you people only. So hope this is understood and this is clear for everybody. That 40 marks is very, very important. So passing this subject is not a difficult thing, but you need to put your efforts. You need to put your effort. That's all. Anybody has any difficulty in this analogy? Okay. Then we have solved some of the problem. Okay. First was this analogy. Second was this just interface flux in heat transfer, and third was this thing. Okay. So what is the answer for this? Roll number 16.
Yes, sir. I got a
Roll number 16. I told. Who is talking? Roll number 60 is talking.
Yes, sir.
Okay. Tell me 60.
Sir, I got 62,000 28 watt per meter square Kelvin as
Okay.
average heat
28
transfer
watt per
coefficient.
meter square. Okay. Now you solve this problem. Everybody take down this given data. So this is also based on interface flux in heat transfer. So most of the problems solved on interface flux on heat transfer because it is very easy to understand this heat transfer. That is what you need to know. And now we have created our understanding, we have generated our understanding that heat transfer is similar to mass transfer is similar to momentum transfer. So similar problem in mass transfer you should solve with same efficiency and same easiness. In momentum transfer also you should be able to solve. Okay, take down all the given data and solve this problem. Abhijit, roll number 70, Abhijit. Roll number 70, Abhijit. Roll number 68, Mitu.
Yes, sir.
Yeah, can you just give outline how to solve this problem?
Sir, first we have given an equation which is in watt per meter cube, but and so we can calculate the heat generation for the entire mass of that aluminum sphere. Like it is given in per unit volume, so we can multiply by area. Then we can integrate it from
Very good.
zero to
Yeah, this is
zero
what.
point 0.2 to
Uh,
0.5.
yeah, in spherical coordinate system and in cylindrical coordinate system, so heat generation
Yes,
will change with the R.
yes, sir.
Okay, this is what the you can say important point to note in that problem. Heat generation, even though it is constant for overall body, but it will change. It is a function of R. It is a function of R. So it will change as per R. So that is what you need to integrate it over R. So and accordingly you need to handle that heat generation per unit volume. Okay. So exactly what he has told, that is correct. So you can follow this. Yeah, anybody got the answers?
Yes, sir.
Yeah, what is the answer?
92.25 degrees centigrade.
Very good. I think it is correct. So we'll see.
Excuse me, sir.
Yeah, tell me.
Sir, can we not approach this problem by heat balance, normal heat balance, like input minus output plus generation equal to 0?
Yeah, that is what we are doing. But here actually heat generation is given. Na? That is varying
Sir,
with R. Exactly, that is
okay.
what we are doing. But
Sir, but
here
R,
R
if we
is a
take it to
function
be
of this.
surface,
Heat generation is a function of R.
sir, but can we take R to be 50, 0.5 meter and then
No, no, no,
uh,
no. It cannot be. So that will give you heat generation at 0.5. 0.5 or heat generation at zero point 0.2 centimeter. But I want what will be the total heat generation between 0 0.2 meter to zero point 0.5 meter.
right, sir?
Okay, so it is not heat generation at zero point 0.5. It is heat generation between zero point 0.2 to zero point 0.5 meter.
Okay, sir. Right, sir.
Okay. So anybody not getting this answer? Yeah, somebody has some problem. So this is what I am telling. Okay, so we have inner radius is zero point 0.2 meter and outer radius is zero point 0.5 meter. If I am taking a heat generation at zero point 0.5, so it will be at this layer only. Okay, at this layer, what will be heat generation? If I am taking zero point 0.2, it will be heat generation at inner layer. But actually, I want what is the heat generation from this point to this point. This is inner radius is zero point 0.2 centimeter, outer radius is, this is what we are doing. So rate of energy in rate of, so there will be total rate of energy generated in the spherical shell. So this spherical shell start at 20 centimeter and ends at 50 centimeter. So that will be rate of energy out. So you can use rate of energy generation is given, so you can integrate. Okay, it is constant over 0 to pi, it is constant over 0 to 2 pi. So theta and phi is, you can say, it is not changing with theta and phi. So you can directly take, because this is spherical coordinate system. So if you remember how to get the volume of spherical volume of sphere in spherical coordinate system, this r square sine theta everything will come actually. And this is whatever I want to sum it over a given volume. So this mathematics I will not go in detail. So this r square sine theta, so theta will come with sine theta will come with theta and r will come with dr. And you, if you want to integrate this over volume, so this will give you, okay, this will give you volume of a cylinder, spherical shell. Volume of a spherical shell, r square sine theta dr d theta d phi. So if you say instead of this you take 1, and if you integrate r square sine theta dr d theta d phi, where r varies from ri to ro, and theta varies from 0 to pi, and 2 theta phi varies from 0 to 2 pi. So you will get a volume of a spherical shell. Okay, spherical shell. And this will be heat generated per unit volume. Okay, heat generated per unit volume. So this multiplied by this, you will give rate of heat generation in the shell. Rate of heat generation in the cell. So and you can see what is subjected to. So inner, this is the rate of heat coming, you can calculate. For here this area will be at zero point 0.2 meter, 0.2 meter. So multiplied by area of a sphere, inner surface area, that will give me rate of energy coming in plus rate of energy added, that will give me rate of energy going out. So what is the rate of energy from this surface, outer surface? Roll number 66, Aryan. What is the rate of energy out here? Aryan,
Sir? Yes, sir.
rate of energy
Sir,
out.
at outer surface, it will be a surface area into the energy into temperature, means it will be 4 pi into radius of its 0.5 square into 150 into temperature minus TW minus 25.
Yeah, but what is value you got here?
Sir, it will be temperature is 92 point.
No, not temperature. First, you might have got na rate of energy in is given. This you have calculated using this formula. This plus this will give me this.
Total, yes, sir.
Yeah, yeah. What is that? This is how much this give? This is rate of
Sir,
energy coming in.
sir, it will be 4 pi into 0.2 square into 15,000.
Yeah, what is that value? I am asking the value.
Sir, I directly calculated that. Means plus 24,120, and I got the final answer.
Okay, what is this final answer then? Rate of energy out.
Sir, it will be 31,659.82.
And temperature you are getting correctly?
Temperature is, sir, 92.18
Okay,
degrees Celsius.
it's correct. So anybody is not getting this? Now this is also
Excuse me, sir.
similar. Yeah,
Excuse me, sir.
yeah, tell me.
So can we solve this problem in this way? Like, can we take a differential volume, r distance from center, and we can calculate the uh, dq, that is total heat of that differential volume, that is volumetric heat generation into dv.
Yeah,
Change 4 pi r square into dr into that is 4.5 into 10 raised power 4 into 1 plus 0.6 r square, and integrate this volume, integrate this heat from 0.2 to 0.5, and the limit for dq will be 1500 to upper limit, that is 115 to t minus 25.
yeah. So do you think whatever you are telling and this method is different?
Uh,
It is
no, sir.
not different. It is same thing. Na? What you are telling is same thing.
Uh, yes.
So if you integrate r square theta d theta d phi, and 0 to pi, 0 to 2 pi, whatever constant you are telling, you will get same thing.
Yes, sir.
So your method and this method is not different. Only just the thing is okay. So instead of a plus b plus c, you are doing b plus c plus a. So you are just changing the sequence. That's all. Otherwise, it is one and same thing. There is no different at all. Difference at all.
Okay, sir. Thank you.
Anybody else got any other idea to solve the problem? Maybe there, in mathematics, this is the beauty of mathematics, I will say, and you can say you can have more than one way to solve any problem. You can have. So in differential equations also you might have seen, while solving differential equation there can be more than one way out. So and mathematics is an integrated part of engineering, and when comes to engineer also can add their thinking. So there can be more than one way to solve any problem in engineering. So anybody, but whatever you told is same thing, only the sequence you are changing, that's all. Okay, this is the solve this problem. So this is again same thing. Only the thing is now here heat generated per unit volume is not function of R. It is given total. Okay, watt per meter cube. Heat generated per unit volume is given total. So and nuclear fuel element is given. It is not hollow nuclear element. So it is given 20 centimeter diameter. And Temperature distribution is given now here. So calculate the thermal conductivity of nuclear fuel element and the average heat transfer coefficient at the surface of the sphere if ambient temperature is 35 degrees Celsius. As I am telling, okay, we are solving the problem in heat transfer. It doesn't mean that, okay, we are doing heat transfer subject again. Okay, this is just to improve our understanding of interface flux in heat transfer. Meantime, so we got all our understanding that heat transfer is similar to mass transfer is similar to momentum transfer. So similar problem can be given on momentum transfer also and in mass transfer also. Equivalent problem can be given. So that you should be able to solve with the same easiness and same efficiency. Roll number 69, Mehul.
Yes, sir.
Yeah, can you just briefly explain how to solve this problem?
Sir, in the similar way as we did in the previous question,
Yeah, but here actually, what is the difference I told?
uh, here the temperature is also varying with respect to distance.
Okay. So how to get the thermal conductivity?
Uh,
Think over and let me know. Roll
yes,
number
sir.
69, Mehul. Okay, think over
Yes.
this and let me know how to get the thermal conductivity.
Sir, we can use the equation Q is equal to minus K into dt by dr. So for that, we'll have to differentiate the temperature equation first with respect to R.
Yeah, Mehul,
Yes, sir.
got
Sir,
the
I was
idea?
saying,
Yeah,
yes, sir. I was saying that we can use the equation Q is equal to minus K into dt by dr.
minus K
So
into dt by dr. Very good. So I can get dt by dr at R equals to
20
20.
centimeter.
Okay, dt because t is given, so you can get
Yeah.
dt by dr that is estimated at r equals to 0.2 meter. So
Yes, sir.
r is in meter. Yeah, r equals to 0.2 meter. So you got dt by dr. So how to get q?
Uh, so Q is equal to uh,
How to get q? So I
sir
have
for Q
yeah, yeah. How to get q?
uh,
Maybe?
for for Q we can use we are given the heat transfer per unit volume we are given. So
Okay.
we can use the equation Q by V is equal to minus k into 4 pi r square into dt by dx into 4 pi r cube. So from that we get q by v equals to 2.4 into 10 raised to 6 watt per meter cube.
Okay. So look,
And
the
when
heat,
once we get,
this is the heat generated per unit volume.
yes sir,
Okay. And what is the, this is a nuclear fuel element. Okay. This is not
yes sir,
hollow spherical ball, 20 centimeter diameter. So you have a volume of nuclear fuel element. What is the volume of nuclear fuel element?
4 by 3 pi r cube.
Okay, so 20 centimeter is the diameter. So you can
Yes sir,
calculate volume of nuclear fuel element multiplied by heat generated per unit volume. So what you will
yes sir,
get? So
q,
to that is not Q. That is Q by that is Q. Okay, that
yes
is
sir,
Q. Small Q or capital Q?
capital Q sir,
Very good. Capital Q. So
yes
once you have capital Q, how to get small q in Fourier law of heat conduction?
uh,
Capital small q is a flux.
yes sir.
Capital Q is a
So
rate.
yeah,
Yeah, how to get the flux from rate?
we can multiply it by area.
Not multiply. Divide it.
Divide by area, sorry. Divided
Divide.
by area, yeah.
So divided by area, which area? Surface.
Surface area of the sphere.
Okay. So what is surface area of the sphere?
4 pi r square, sir.
4 pi r square. Okay. So then you will get. So what is?
The value of k we can get by substituting it in the previous equation,
Okay.
which
So
is
what is the rate you are getting? Rate of heat transfer at the surface.
uh,
Okay.
just a
Okay.
second, sir.
Okay. Okay. Mehul. Fine. Fine.
Yes, sir.
Roll number 54. Deepshikha.
Yes, sir.
What is the rate you are getting?
Sir, one minute. Uh, sir, for B now. Hello.
Yeah. Yeah.
Sir, it is
Where is your A? Have you solved A?
sir. Sir, I did in different way, I think.
Okay. Okay. So tell me your different way. Tell me your different way.
Sir, what I did is the Q energy equals to energy flux equals to Q by 4 pi r square, and sir, Q dot equals to Q by 4 pi r cube. So so my Q dot value, that is the rate, equals to 3Q by 4 pi r square into r. So I put it the value of Q by 4 pi r square as QR. So the rate becomes 3Q by r.
What is the
So
thermal conductivity you got?
sir, thermal conductivity is 40 watt per meter Kelvin.
Anybody else getting this 40? Yeah. Number 60 also got same thing. Anybody else is getting this 40 other than 40 watt per meter Kelvin?
Yes, excuse me, sir.
Yeah, tell me.
Sir, previously also we had solved such a problem. So in that problem we did, if whenever we had watt per meter cube, we took G is equal to
No, no,
K
no.
into.
Look. There it was a given. This G was varying with R. If you go to this, okay, G is a function of R. Can you see here?
Right, sir.
It is given G is a function of R. Here I cannot straight away take the volume because volume is changing with R. Volume is a function of R. But in this
Sir,
problem, it is given G is watt per meter cube for
sir, yes,
this spherical
G is
element.
equal, G is equal to K into D2T by D y square.
Okay.
So from that we can get d2t by dy square. So we have g. So we can find k.
Yeah, that's also fine. What is the value of k you got?
Sir, it is coming to be 120.
No. You should get same thing.
Okay, sir.
You should
Sir,
get
it's
same
coming
thing.
120 by that method. For me also.
But actually there the d2t by dr. Yeah, I think you should get same thing. Somewhere you might be doing mistake. So you are using r is in centimeter or something.
Sir, r would not remain, I guess. So, for first derivative, it would become minus 20,000 r. Then for second derivative, it will remain minus 20,000.
Okay, it will be 2.4 into 10 raised to 6 be divided by 20,000.
Right, sir.
No, actually that k equals to d2t by dr square. That is for flow or flow cubical geometry. That heat generation in cubical geometry. That is actually.
Sir, but to derive this also, area got cancelled. So
No.
it
How
can be.
area will get cancelled? Area is a function of r, na?
Oh, okay. Yes, sir.
Area is a function of r here. Their area is not function of length.
Yes, sir. Got it.
Okay, that is for that equation is true only for a slab. Okay, rectangular geometry where surface area is not function of length. But here surface area also you need to take into account.
Right, sir.
Okay, so that if you take into account, so you should get same thing.
Yes, sir.
And now you got a rate of heat transfer at the surface, and that will be equals to h into tw minus T infinity. T infinity is given, so you can calculate the surface temperature. No, surface temperature you can calculate here. Temperature at R equals to 0.2. What is the surface temperature? Yeah, roll number 47, Gurupreet.
Yes, sir. I got 800, sir.
800.
Yes, sir. Sir, surface temperature.
Okay.
800.
And what is heat transfer coefficient you got?
Sir, 104.57 watt
Yeah,
per meter
I
square
think that is
Kelvin.
correct. Both are correct. So thermal conductivity is 40 watt per meter Kelvin, and heat transfer coefficient is 104.6 watt per meter square Kelvin. So anybody else is getting any other answer? We can discuss that also. If anybody is not getting this answer, can come forward and clarify whatever doubts you have.
Hello, sir.
Yeah, tell me.
Roll number 40, sir.
Tell me.
Sir, I'm not getting the answer.
This you have this 2.4 into 10 raised to 6 watt per meter cube.
Yes, sir.
What is the volume of a sphere?
Sir, I got 4.19 into 10 power minus 3 meter cube.
Meter cube, na? How you
Yes,
are
sir.
calculated? 4 by 3
4 by 3 pi r cube.
pi r cube. Okay. Now this multiplied by volume,
Yes, sir.
you will get rate.
Yes, sir.
So rate at r equals to 20 centimeter. What is the rate at r equals to 20 centimeter? It will come in watt.
Yes, sir. 10,056 I got, sir.
Okay. Divided by area, surface area of this nuclear fuel element, outer surface area. What is that surface area?
0.126, sorry, 0.126 meter square.
How you have calculated?
4 pi r square, sir.
4 pi r square. So you divide whatever rate you got in watt per meter square. Okay.
Yes, sir.
That you got flux.
Yes, sir.
What is flux you got?
79,000 809.5 watt per meter square, sir.
Okay, now dt by dr, use this equation T, and what will be dt by dr? Dt by dr will be 900 minus 20,000 into r, and
Sir,
put
it will be
r equals to 0.2 meter.
dt by dr will be minus 20,000 into
Not
0.1.
minus 20,000, dt by dr. It will be 900 minus 20,000 into 0.2.
Sir, on first time differentiating 900 is a constant. It will be
Okay. Yeah. dt by dr is a minus 20,000 into 0.2. Okay, and
yes,
whatever
sir.
flux you have got divided by this dt by dr, you should get k. This value of k, 40.
Yes, sir.
Now getting?
Yes, sir.
Okay. Now you have this value k, you have already got. Now you have rate of heat transfer at the surface. Already you have in watt.
Yes, sir.
Okay. And this flux also you got at the surface.
Yes, sir.
Now this flux also equals to H into delta T.
Yes, sir.
Okay. And delta T, how to get delta T? I will get surface temperature using this equation. Substitute R equals to 0.2. That will give me surface temperature. 900 minus 10,000 multiplied by 0.2 square. So somebody told that, okay, surface temperature is something around 800 degrees Celsius or degree Kelvin. Degree Celsius, you can take degree Celsius. 800 degrees Celsius. Are you getting this 800 degrees Celsius?
Yes, sir.
So now this flux will be equals to, okay, flux will be equals to H into 800 minus 35. So you can get heat transfer coefficient.
Yes, sir.
Now you are getting this 104.6.
Yes, sir.
Okay. Might be some calculation mistake. So you do step by step. That is what I am telling. So don't adopt any shortcuts, because these problems are very simple. So very fundamental way I will tell, to solve any problem in engineering, any problem in any subject, you take down all the data with standard nomenclature. Like here, radius of fuel element is small r equals to zero point 0.2 or 20 centimeter, that is equals to 0.1 meter. Temperature, this degree Kelvin. Everything you take down in a standard nomenclature and observe the given data. So certainly, if you have something in mind, some model equation, so relating all this, that will come in your mind straight away. Because I want K, G is given, R is given. Certainly, I need a rate, or I need a flux, I need a dt by dr, that can be calculated, flux can be calculated, hence K can be calculated. So it means that I need to use Fourier law of heat conduction. Then here, heat transfer coefficient I need, H I need, delta T. From where I will get delta T? One temperature is given. So certainly other temperature can be estimated here. Again, I have flux, so I can use Newton's law of cooling and get the heat transfer coefficient. So which equation can be used? That already you will have some outline idea from the given data itself. So given data and missing data, if you just observe it carefully in standard nomenclature. But nomenclature should be standard. Standard means which is people are using. If you write say temperature equals to small t, then you will get confused. Okay, dt by dr, a small dt by dr. So if you observe missing parameters and given parameter, certainly which equation, model equation, which law need to be used, it will be clear in your problem itself. And solve problem step by step, one by one. Don't try to get the answer in one step itself. So in that way, so maybe you will spend more time. You'll spend more time, but chances of getting wrong will be negligible. There is negligible chance of getting wrong if you are solving your problem step by step. If you are embedding everything in one equation itself, then okay, so there is a probability that you will get correct answer also. 50-50 chances will be there, even if you miss simple thing. Here, what is the probability of missing is, instead of using this R in meter, you will use R in centimeter. That is the only one mistake you can make here. Other mistake will be using the formula for volume of sphere, using the formula for surface area of the sphere. That these are the three important points where you can make a mistake in this problem. Otherwise, this problem is very uh, nothing to do with heat transfer, nothing to do with mass transfer, nothing to do with momentum transfer. So if you remember that this R is in meter, given R is in centimeter, what is the volume of sphere, how to get the volume of sphere, how to get the surface area of sphere, there is no chance that you will get wrong answer. Everybody got this answer? Anybody not getting this answer still? Okay, now you solve this problem. Now this is plane wall. Now here that analogy can be, if it is a plane wall, a surface area is 30 meters square, thickness is 20 centimeters, separated by hot fluid. So 170 degrees Celsius, and cold fluid is at 15 degrees Celsius, steady state condition. Temperature is given, and yeah, here you can see rate of heat generation within a wall. Here that d2t by dx square will come, because this is the plane wall. Plane wall, and this surface area is not function of thickness. Okay, surface area is 30 meters square constant, but it was not the case in spherical coordinate system and cylindrical coordinate system. There it will not be the, so you need to, you can have this k d2t by ds square, but a k by a will be there. That a will go in a differentiation actually, d by d x square of t square divided by a. Okay, that you need to consider when you are using similar formula for spherical coordinate system or cylindrical coordinate system. Take down all the data in a standard nomenclature like area, capital A, thickness. Here thickness is given, but as per as our nomenclature, you can write like a L, because length generally we are using, or you can use thickness also, but remember thickness, you can say thickness and then length into width is a area. Separated hot fluid, okay, bulk temperature of hot fluid is 170 degrees Celsius, and bulk temperature of cold fluid is 15 degrees Celsius. So calculate the average heat transfer coefficient at the hot and cold surface, where x is the distance measured in meter. So here again same thing, thickness is given in centimeter and this distance is measured in meter. T is the temperature in degree Celsius. So if thermal conductivity of wall is 10 watt per meter Kelvin, calculate the average heat transfer coefficient. Here roll number 21, Sai.
Sir,
So how to go for this problem?
we have here it's given, sir. Distance plate varies from 0 to 0.2 meters. So
Okay.
at T, we can do like at T is equals to 0, temperature is 150 minus 600 equals 50 x square. At T2, that is at X is equals to 0, we will get 150 degrees centigrade. And at X is equals to 0.2, we will get 28 degrees centigrade.
Okay.
From this, we'll substitute heat transfer coefficients like H into delta T is equals to hot surface is equals to cold surface. If we equate these temperature differences, we will get heat transfer coefficient at hot surface and at cold surface, sir.
Okay, but how to get flux?
Sir?
How to get flux?
Uh,
Flux will be equals to H into delta T.
delta T, yes, sir.
So now you got delta T.
Yes, sir.
So
from this we will get delta T.
okay, and how to get then flux? Small q.
Small q is equals to if we Ka into by area, I mean the distance, sir. Q is equals to Ka into delta T2 minus T3. Like at T is equals to 0.2 minus T is at 0. X is equals to 0.
K. K into delta T.
Area, sir. Area, sir.
No. K into area. So you can see K is in watt per meter Kelvin. If you multiply.
Yes, wrong, sir. No,
So how
no.
to get flux?
KT dx by dx. K
Yeah,
into dt by dx, sir. K is
exactly.
given.
So you get the flux on hotter side.
Yes, sir.
That will be K into dt by
dt by
dx
dx.
at x equals to 0.
Yes, sir.
That will be a flux at hot
Yes.
side flux. And K into dt by dx at x equals to 20 centimeter, that will be a flux at cold side.
Yes, sir.
Okay. So, and as you told, flux will be equals to H into delta T. So one temperature is given. So I can calculate temperature at x equals to 0. That will be hot side temperature. So 170 minus 150. Okay, that will be delta T, and flux already minus K into dt by dx.
Yes.
Minus dt by dx. So that will give you a heat transfer coefficient on hot side. So similarly, minus K into dt by dx at x equals to 0.2 meter, that will give you flux, and one temperature is 15 degrees Celsius, another temperature will be T 150 minus this multiplied
20.
by 0.2 you can keep. What will be temperature, surface temperature on cold side?
20 degrees centigrade, sir.
28 degrees Celsius. So delta T will be 13. So you can calculate the heat transfer coefficient on cold side.
Yes, sir.
So what will be the heat transfer coefficient? So you can write in chat box if somebody is getting the answers. Hot is 300 watt per meter square Kelvin and cold is 476 watt per meter square Kelvin. Roll number 18, Ashish got this. 300 and 476. Yeah, 300 and 469. So cold will be 469. The hot is 300. Everybody is getting 300. So I think 300 is correct. And how about cold side? 476. So 476, 77. So I think you check the answer, Ashish. 76. What Ashish got? 476. No. Yeah, 476 only. 69. Siddesh. Siddesh? So you
Yes, sir.
got 69. 469. Something wrong.
469.23.
No, that is wrong. You check where you are make a mistake. $469. Almost everybody is getting 476. 76, 77 is fine. But 469, somewhere you are done wrong. Siddesh, you check. and determine the rate of heat generation within a wall. Here you can use that minus k d2t by dx square because area is constant. Okay, area is constant. So rate of heat generation per unit volume will be minus k d2t by dx square. d2t by dx square will be a 100 multiplied by 10, 600 watt. Oh, determine rate. Yeah, very good. So it is not per unit volume multiplied by volume of this thing. Rate of heat generation within a wall multiplied by volume. How to get a volume? So it will be a area multiplied by thickness. So area is 30 meter square multiplied by thickness is 0.2. So it will be a 0.2, 6 meters cube, 6 meter cube. 6 multiplied by 1000 watt per meter cube, 6000 watt. Almost everybody is getting correct. Have you corrected that answer? Who was getting wrong answer? This very fast people are typing. Yeah, Siddesh,
Yes, sir. Got it.
where you have made the mistake?
Sir, temperature difference, sir. It was 120. I took 122 by mistake.
What 120?
Sir, sir, hotter side surface temperature was 150, and that surface temperature was 28 degree colder side. So, sir, difference I took.
That difference you took. Okay. So you should take 28 minus 15.
Yes, sir.
So you can draw a sketch also while solving the problem. Rough sketch here 170, here 15, and so on. So these are all tricks not to get a wrong answer. So taking data, writing equation, solving step by step. These are all tricks not to get a wrong answer. Okay. So it is 300 watt per meter square Kelvin. Hot heat transfer coefficient. Cold heat transfer coefficient is 477 watt per meter square Kelvin, and rate of heat generation is 600 watt. So here itself you can see heat transfer coefficient on hotter side, heat transfer coefficient and cold side. So heat transfer coefficient is not a property of material. It is a property of system. So because you can see this wall is there, and again this fluid is same on hot side and cold side. Wall is same on hot side and cold side. It doesn't depends upon heat transfer coefficient, doesn't depends upon this wall and fluid only. It depends upon a property of system, other property of system also. While thermal conductivity of wall is same. Okay, it is 10 watt per meter Kelvin on hotter side also, in cold side also. So this is called as the property of material. So this is thermal conductivity is the property of material, while heat transfer coefficient is a property of system. It is not a property of material. So you can get a different heat transfer coefficient in combination is same wall and fluid, same wall, same fluid. Hot side you got different heat transfer coefficient, cold side you got different heat transfer coefficient. But thermal conductivity, you can see it is thermal conductivity at x equals to 0 also 10 watt per meter Kelvin, at x equals to 20 centimeter is also 10 watt per meter Kelvin. So even though if you go in details of thermal conductivity is also function of temperature. But here temperature is varying only from 28 degrees Celsius to 150 degrees Celsius. Maximum is 150 degrees Celsius. So during this say 100 degrees Celsius variation, 100 to 100 degrees Celsius variation, there is a negligible variation of thermal conductivity. But thermal conductivity is again a property of material. Thermal conductivity of copper, I can say. Thermal conductivity of plain wall, I can say. Thermal conductivity of water, I can say. thermal conductivity of air I can say, but I cannot say heat transfer coefficient of water, heat transfer coefficient of air. I cannot say. It is a property of system, whole system I need to define. Based on that only I can judge the heat transfer coefficient. Okay, so this is the summary of what we have covered. So now maybe couple of classes I will make you realize that okay, these are the thing. So what we have done till now is a flux. We have started our subject with a flux, then we have discussed convective flux and molecular flux, and then summation of this flux you will get a total flux, and this total flux at interface you will get an interface flux. While discussing this molecular flux, while discussing this molecular flux, we got three dimensionless number. So Prandtl number, Schmidt number, and Lewis number. Then ratio of convective flux to molecular flux. Convective flux to molecular flux, we got Peclet number for heat transfer and Peclet number for mass transfer. Then we have an interface flux. So interface flux, so there we have in this molecular flux we got three laws. So Newton's law of viscosity, Fourier law of heat conduction, and Fick's law of diffusion. In interface flux we got three equation again: Feining equation, Newton's law of cooling, and a Slattery equation. Okay, so there again we got a two dimensionless number. While discussing the ratio of you can say transfer coefficient, ratio of transfer coefficient gives Stanton number for heat transfer and Stanton number for mass transfer. Ratio of fluxes will give me a Nusselt number, Reynolds number, and Sherwood number. So these are the 10 dimensionless number with a physical significance we have discussed till now. Prandtl number, Schmidt number, Lewis number, Peclet number for heat transfer, Peclet number for mass transfer, Stanton number for heat transfer, Stanton number for mass transfer, then Nusselt number, then Reynolds number, and Sherwood number. Then this Newton's law of viscosity, there we have discussed viscosity. Then this viscosity, where viscosity we have discussed in Newton's law of viscosity. Thermal conductivity is discussed in Fourier law of heat conduction, and Fick's law we have discussed diffusivity. Similarly, Feining equation we have discussed friction factor. Then Newton's law of cooling we have discussed heat transfer coefficient, and Slattery equation we have discussed mass transfer coefficient. So everywhere we found that velocity profile, temperature profile, and concentration profile are important. So as I told previously also, so these are the 9 most important thing we'll be discussing hereafter. So estimation of friction factor, estimation of heat transfer coefficient, estimation of mass transfer coefficient, then estimation of diffusivity, estimation of viscosity, estimation of thermal conductivity. Okay, and then almost from remaining classes, almost 80% of the time we'll be dealing with how to get the velocity profile in momentum transfer, how to get the temperature profile in heat transfer, and how to get the concentration profile in mass transfer. And there are some other thing we have discussed, power, drag force, and this characteristic property, what is meant by characteristic length, characteristic velocity, and all. This is what already we have covered. Now we'll move on, and then we have also discussed analogy. So what is the analogy? So analogy is an interrelation between two areas. So here initially we have developed our understanding that these three areas are similar to each other. Then we have introduced the analogies which are telling me that okay, these three areas are similar, but subjected to some situation, limiting cases, these three areas are equal. These three areas are equal. So it means that given a data in heat transfer, I can estimate all the property in momentum transfer. Given a data in heat transfer, I can estimate all the property in mass transfer. There, that is what the importance of analogy is there. So now, this is what our remaining thing is there. So we'll be discussing first evaluation of transfer coefficient, friction factor, heat transfer coefficient, and mass transfer coefficient. Then thereafter we will discuss the evaluation of transport property, viscosity, thermal conductivity, and diffusivity. And then the remaining classes will be devoted for getting the velocity profile, temperature profile, and concentration profile. Now in today's class we will be briefly discussing how to get this friction factor, heat transfer coefficient, and mass transfer coefficient. Okay. So as I told, friction factor, heat transfer coefficient, and mass transfer coefficient is a property of system. So even if you are changing a velocity, these properties will change. Friction factor, heat transfer coefficient, mass transfer coefficient will change. If you change temperature, again it will change. So it is very customized for given system. So certainly there is no theoretical derivation to get this friction factor, heat transfer coefficient, and mass transfer coefficient. So we need to rely on an experimental observation only. So that is what I am telling, that there are thousands of analogies available, thousands of engineering correlation available, because as soon as experimental observation put into equation, that kind of theory is given, that is called as the engineering correlation. So you can have a different system, different equation, different system, different equation. So we need to rely on experimental observation only for getting these values: friction factor, heat transfer coefficient, and mass transfer coefficient. So certainly equation for this, getting the friction factor, heat transfer coefficient, and mass transfer coefficient will change from system to system. It all depends upon, okay, so robustness of the given equation to estimate this friction factor, heat transfer coefficient, mass transfer coefficient depends upon the range of the experimental observation which is considered while doing the experiment. So here, these are all called as the engineering correlation. So this is called evaluation of transfer coefficient, and these all are engineering correlation. So it is not a theoretically derived equation. These are the experimentally observed equation put into model form. That's all. So there is no theoretical solution available for getting the value of heat transfer coefficient, mass transfer coefficient, and friction factor. These are transfer coefficient. These are termed as transfer coefficient. No theoretical solutions are available. We need to rely on experimental information only. Experiments are done for getting the value of friction factor, and that put into equation. So there is a slight engineering involved in this. Otherwise, this is just a polynomial fitting. Okay, what is this equation which we are getting for estimation of this transfer coefficient is a polynomial fitting, but slightly engineering inputs are involved in this, hence it is called as the engineering correlation. And you might have used these engineering correlations in so many subjects. Some correlations will be there, so there will not be any meaning to that constant, whatever a, b raised to c, and d raised to e. So that parameter doesn't have any meaning. So that you can say polynomial fitting. If some parameter has some engineering importance, then you can call it as engineering correlation. So if some engineering inputs are given, so generally this transfer coefficient. So whenever I am discussing transfer coefficient, so dimensionless numbers are used. Okay, dimensionless numbers are used. So dimensionless number plays an important role in engineering design. So that is why it is called as an engineering correlation rather than polynomial fitting. Okay, so whatever equation which we are going to use for estimation of transfer coefficient, so rather than just calling it as a polynomial fitting, it is called as an engineering correlation because these dimensionless numbers are used there actually. So and whenever you are using this engineering correlation, you must know the limitation of that engineering correlation, because these engineering correlations are derived using experimental observation, and this experimental observation limiting value of experimental observation is nothing but the limitation of this engineering correlation. So that is what it is, limited to given parameters. Okay, given parameters. So that also very important along with engineering correlation. So there can be more than one engineering correlation for same system. If different scientist is doing the experiment, they can put their experimental form in different forms. So you can have different engineering correlation available for similar system, and there can be error as high as plus minus 20%. So this is huge error, you can say. Huge error as high as plus minus 25% in estimation of this transfer coefficient if you are using two different engineering correlation. Okay, two different engineering correlation. This is why, because of this, all 4 points, experimental, how excellent you are in experiment, that is also considered in this error. What kind of engineering input you are giving to your experimental observation, that is also added in this error. And again, limitations. So if it is the range is very small, you can have very accurate value. If say range of your experiment is very wide, say I am discussing something for Reynolds number 0 to 10,000, so certainly if I am using it for 10,000, if you are using it, I can use it for 1,000 also, I can use it for 0 also. So error will be higher. While some other equation which is true only for Reynolds number less than 2100, or Reynolds number between 2100 to 3000, Reynolds number likewise. So if ranges is smaller, so it will give lesser error. So that also you need to understand. So when I am using two different engineering correlation, there can be a error of plus minus 25%, as high as plus minus 25%. So this is what we will be doing. We will be studying how to estimate the friction factor, how to estimate the heat transfer coefficient, and how to estimate the mass transfer coefficient. And most common engineering correlation format of engineering correlation for estimating friction factor is of this. Friction factor is a function of Reynolds number. Okay, so you will get engineering correlation of this format. Friction factor is a function of Reynolds number with some constant here and there. Some say A Reynolds number raised to B equals to friction factor. Most common, and A and B are different for different system. Similarly, Nusselt number is a function of Reynolds number and Prandtl number. So you can say A into Reynolds number raised to B plus or into Prandtl number raised to C. Okay. Likewise, you will get Nusselt number, and Nusselt number here you will have heat transfer coefficient. Nusselt number is HL by K. Okay. Similarly, Sherwood number is a function of Reynolds number and Schmidt number. This will be the engineering correlation for estimation of mass transfer coefficient. So in Sherwood number, you have KL divided by DAB. KL divided by DAB. Sherwood number is K into characteristic length, Kc into characteristic length, not K, Kc, mass transfer coefficient into characteristic length divided by DAB, that is Sherwood number. That is a function of Reynolds number and Schmidt number. And already you have seen all these three types of engineering correlation. This type of equation you might have come across in fluid mechanics. This type of equation you might have come across in heat transfer. This type of engineering correlation you might have come across in mass transfer. So these are the equations which we are using to get to get the value of heat transfer coefficient, mass transfer coefficient, and friction factor. So this is clear up to this point. So what are engineering correlation? What is you can say generalized equation or generalized engineering correlation available to get this transfer coefficient in heat transfer, mass transfer, and momentum transfer. So briefly, what is the limitation of engineering correlation and everything? Anybody has anything to discuss over this point? This slide, given slide.
Hello, sir.
Yeah,
Can
tell
you
me.
please can you
Roll
please
number.
repeat
Roll
roll
number.
number 60?
60. Yeah. So what
Uh,
exactly you
s-
want to know?
Sir, the point limitation, sir.
Yeah, limitation, because you can see friction factor is a function of Reynolds number. So this you have Nusselt number is a function of Reynolds number and Prandtl number. Do you remember that Deters-Bartle correlation?
Uh, Sorry, sir, I
Nusselt
don't remember.
number, Deters-Bartle correlation. Okay, just I will show you that Deters-Bartle correlation. Screen. So do you remember this Nusselt number equals to 0.023 into Reynolds number raised to 4 by 3, Prandtl number raised to n. So n is equals to 0.4 for heating, n equals to 0.3 for cooling.
Yes, sir, I
So,
remember.
so I cannot use this equation. Nusselt number equals to 0.23 Re raised to 4 by 3, Prandtl number raised to n anywhere. So this is true for where it is true for.
For sir, the limitation Reynolds number greater than equal to 10,000
Yeah, Reynolds
and
number
Prandtl
should be
number.
greater than 10,000. You can say turbulent flow.
Yes, sir.
Then Prandtl number between 0.7 and 60.
160. Yes, sir.
And L by D is greater than 10.
Okay, sir,
Okay.
got it.
This
Yeah.
is also one limitation. So
Yes,
first
sir.
of all, this is limitation. For heating, for cooling, values are different. Then Prandtl number should be between 0.7 and 60. Reynolds number should be greater than 10,000. L by D should be greater than 10. And one more important limitations. What is the important limitation for Dittus-Walter correlation? Most importantly. Yeah, anybody?
Flow through circular pipe.
Yeah, very good. So it is true only for flow through circular pipe. So you cannot use this correlation for flow over flat plate. Okay, you can see this is 4.5. This is 4.5 and you can see this 4.5 is a heat transfer correlation, and then you can go in here, see the 4.2, 4.5 is true only for flow through pipe. 4.5. So 4.5. So you can say 4.5 is flow in circular pipe. This section 4.5 is for flow in circular pipe. So in flow in circular pipe, these are all momentum transfer coefficient, and then we have heat transfer correlations. Okay. So why these limitations are coming? Why these limitations are coming? That is what limitation is there, because Dittus-Walter has done an experiment for flow through pipe, and they have estimated Nusselt number, Reynolds number, and Prandtl number. They have estimated these values for their experiment and fitted their values and got this constant 0.023, 4 by 5, and n for all their experimental value. What was the range of their experiment? They have done an experiment in a range of Prandtl number. Lowest Prandtl number was 0.7, highest Prandtl number was 160. It was their experimental range. Again, they have done all the experiment for Reynolds number greater than 10,000, and they have done a different geometry. Geometry L by D, all the geometry was L by D greater than 10. So these limitations are coming from their range of experimentation, limitations of their experimentation. So just remembering this equation is not enough. Okay, remembering this equation is not enough. You need to remember these limitations also. First of all, this is true only for flow through pipe. Digital Barter correlation is true for only flow through pipe. And again, for heating, it is different. And this is one thing. Now, hope this is clear for you, this limitation.
Yes, sir, clear.
Okay, and now come to this. Error is in order of 25 plus minus 25. Again, I will go to same example. Now there is one correlation, Dittus-Walter correlation, which is true, and there is one another which is true, Cedar-Tate relation. Now you can see L by D, same thing. Reynolds number should be greater than this. Say this is Prandtl number. This is Prandtl number. Say my Prandtl number is 100. So I can use Cedar-Tate correlation also. I can use Dittus-Walter correlation also for flow through pipe. So if I use this, I will get different value of Nusselt number. If I use this, I will get different value of Nusselt number. Certainly, if I use this Cedar-Tate, I will get different value of heat transfer coefficient. I will get different value of heat transfer coefficient, and there can be a difference of plus minus 25% if I calculate heat transfer coefficient using this, Both are correct. Okay, both are correct. I cannot say that this is wrong and this is right. Okay, if I am using, say, my Prandtl number is say 10,000, then I cannot use this Dittus-Walter correlation. Then I need to use only this Cedar-Tate correlation only, because this is true for Prandtl number between 0.7 to 16,000. For 10,000, this is valid, but for 10,000, Dittus-Walter correlation is not at all valid. For 10,000 Prandtl number, I am using say Dittus-Walter correlation, so certainly this is wrong answer. So this will be correct answer. But say my Prandtl number is 100, Reynolds number is 20,000, L by D equals to 100. Then I can use Cedar-Tate correlation, I can use Dittus-Walter correlation. Okay, and these two will certainly give me different values, and that difference will be plus minus 25%. So it can have, this engineering correlation can have a error of plus minus 25%. Because why? Because these are all a polynomial fitting, and some engineering inputs they have given. They have rearranged all parameter in the form of Reynolds number, Prandtl number, and Nusselt number. This is what engineering input is there. Hence, these are called, rather than calling it as a polynomial fitting, we are calling it as an engineering correlation. So this is not purely polynomial fitting. Some engineering inputs, they have rearranged the parameter in the form of dimensionless number, and dimensionless number have physical significance. So some engineering inputs are given. And if you calculate heat transfer coefficient, if say I can use this, I can use this, or I can use this also. So here also limitations are there. You can say Reynolds number, Prandtl number, and mu w. So if I use these three, so all three will give me different answer, and that difference can be plus minus 25%. That is what I mean to say, error in order of plus minus 25% error. This you should keep in mind. While estimation of heat transfer coefficient, mass transfer coefficient, and momentum transfer coefficient. There can be error because all these are engineering correlation. So hence at the end you need to, for avoiding failure of your design, you will be adding a factor of safety. So for that, this information is very, very important. Error can be plus minus 25%. Even this is error. Shravan, this is error, but this plays an important role. You must know what is the order of error you can make in your calculation. Okay, making error is not very you can say worst thing. Okay, so you need to live with some error, because all engineering started with assumptions. All engineering started with assumption, and assumption is likely to give you errors. But knowing that error is also as important as knowing the equation, model equation. So what is the order of error you can make? Here, if you know that I can make plus minus 25% error, so you can avoid the failure of your design by adding the factor of safety at the end, because you know that order of, otherwise what you can do is unnecessarily you will be over designing the thing. Okay, if say thickness of reactor is needed 1 centimeter, you can use a thickness of reactor equals to 50 centimeter. So what you can say this, okay, because I don't know the values, but now I know the error plus minus 25%. So if thickness is coming into 1 centimeter, so I can add a 50% error, so 1.5 centimeter I can use. But I know that my design will never fail in that case. Is it okay? So anybody else? Anybody else can add anything in this engineering correlation?
Excuse me, sir.
Yeah, tell me.
Sir, previously we had seen Reynolds analogy and Chilton-Colburn analogy, and
Yeah,
we
yeah,
had seen similar things. So
yeah,
why is
yeah.
it that we're calling Reynolds and Chilton as analogies and this Dittus-Boelter as correlation?
Because they are logically correlating two areas actually. What we are doing,
Okay,
okay, in
sir.
Reynolds analogy and Chilton-Coleman analogy, they are logically correlating two areas. Hence, they are called as the analogy. While these are just a polynomial fitting, I can
Sir,
call it
if
as a correlation, simply correlation, Dittus-Boelter correlation. And then engineering is added because some dimensional less number inputs are given into that, hence engineering correlation. These are just a polynomial fitting. These are not a polynomial fitting. These are logically correlating the areas, hence they are called as the analogy.
Sir, so even if I call Reynolds a correlation, that won't be wrong, because even here Nusselt, say Nusselt number is a function of Reynolds and Prandtl, so it is relating to momentum transfer.
No. Here no momentum transfer is there. There is Reynolds number in heat transfer also, na? Will have some
But
different physical significance.
yes, sir.
Okay, so Reynolds number in heat transfer will have some different physical significance.
Yes, sir.
Okay, so Reynolds number in momentum transfer has some different physical significance. Okay, like here there is no two dimension. Here only one dimensional less number is coming into picture. Here two dimensional less numbers are there. So that is what initially also I told that, okay, we are telling that heat transfer is similar to momentum transfer is similar to mass transfer. They are similar, but there are some differences also. And one example also I have given that there is no radiative heat transfer, no radiative mass transfer, and no radiative momentum transfer. There is
Yes.
not at all that radiation heat transfer. You can say that is the most one of the most area of concern for study in heat transfer, radiation heat transfer, radiative heat transfer. But similar kind of transport phenomena is not available in mass transfer and momentum transfer. Similarly, here also, look at these three equation. Here I have only one dimensional less number, but here I have two dimensional less number. Here I have two dimensional less number. So this Reynolds number will have some physical significance in heat transfer also. If you analyze properly, how what is the physical importance of Reynolds number in heat transfer only. So you will get that idea, physical significance of heat transfer in physical significance of Reynolds number in heat transfer.
Yes, sir.
Okay. So with this, we'll start this engineering correlation. So just we'll have some introduction of this engineering correlation today, and actually we'll start in next class. But this is also very important. First of all, motivation. Motivation is very, very important. Why we are studying engineering correlation, and how far we should study engineering correlation. Okay, how far we should study engineering correlation. These all are very, very important. Okay, so many a times I will tell many a students that so admitting in chemical engineering and doing chemical engineering, it is not the thing that you are learning chemical engineering completely. So it is just the you are learning how to learn the chemical engineering, because this chemical engineering is not so small that you can learn whole chemical engineering in 4 years. There is no limits for learning this chemical engineering. You can have unlimited information, vast information is available. So what you are doing in this 4 year is how to learn the chemical engineering. Same thing, that if you know the you can say motivation, limitation, everything about some topic, so you can how the introduction of that topic. So instead of calling this as a chemical engineering, you can call it as an introduction to chemical engineering, whole subject, 4 years, because this is not the only thing available in chemical engineering. It is limitless actually. So same thing, that is what we are going to do today also. So engineering correlation we have done, motivation. So most of the engineering correlations physical, because these are all depend on different physical properties. So physical properties are estimated at some reference. Okay, so heat transfer coefficient, mass transfer coefficient, Reynolds number, Prandtl number, this Nusselt number, this thing, that thing. These all are different parameter dependents. Okay, so there are common references used for estimating these parameters. So sometimes bulk temperature or concentration. Okay, bulk properties are defined in a engineering correlation sometime. So bulk properties, bulk temperature is used, bulk concentration is used, bulk velocities are used. Okay, bulk properties are used, and sometimes film temperature at the surface. So film temperature, film concentration, or whatever the film properties are used at the surface. At the surface properties are used. So certainly it will be mentioned along with that engineering correlation. So whether properties are estimated at bulk temperature or properties are estimated at wall temperature, that will be mentioned. So now how to get the bulk temperature? So bulk temperature, there are different ways. Okay, like flow through duct, flow through pipe. So average temperature and concentration, if the fluid were thoroughly mixed. So if there is a flow through pipes, so average temperature, average concentration, and average velocity is used, is called as a bulk temperature, bulk property. Okay, bulk property, average. And flow or flat plate, mixing cup temperature, sometimes mixing cup temperature. Okay, this is used. Okay, mixing cup, getting the average properties, getting the average property for flow through ducts. Okay, this is the property. Some wetting factor you can use, and this will be average over the area. So that will give you average temperature. Similarly, average concentration, average velocity you can get. Some wetting factor you can use, so that it will be average for a given area, a given region actually. And if you have flow past bodies, okay, so my system is immersed in a fluid, so infinity temperature, okay, far away. If I go far away from my surface, that is taken as a bulk temperature. Okay, bulk temperature. So flow submerged subject. Okay, so bulk temperature will be T infinity. Okay, and so flow or flat plate, flow or sphere, So what will be bulk temperature? Bulk temperature, if I go very far, after which there is no change in temperature, concentration and velocity, that will be taken as a bulk property. Okay. So, and this will be mentioned actually, this will be mentioned in engineering correlation. So maybe in books, sometimes they will not mention, because that, as I have given an example of details by alter correlation, even though it is given over only half a page description of that details by alter correlation, but if you go in actual literature which published by details by alter correlation, it will not be less than say 10-15 pages of research journal. So that is compact form. Sometimes some limitations will not be mentioned. So only important limitations will be mentioned as per your need. That will be the case. So likewise, bulk temperature, whether properties are estimated at bulk temperature, bulk concentration, film temperature, where properties are estimated. So this is how bulk temperature is defined. For flow through pipes, average temperature is taken as a bulk temperature. You can use suitable wetting factor. For flow pass body, a temperature far away from my body will be taken as a bulk temperature. Thereafter, there is no change in temperature, concentration, and velocity. That will be taken as a bulk velocity. And already we have seen an example while discussing that Newton's law of cooling, Fourier law of heat conduction, Newton fixed law of diffusion. There we have seen bulk velocity, bulk concentration, and all. So how it is defined? That just we are putting it in statements actually. Then film temperature. So film temperature. So sometime bulk temperature plus wall temperature, average of this will be called as a film temperature. Sometimes just a wall temperature is called as a film temperature. So this is how different definitions are available. Different definitions are available. Different scientists will define differently. Okay. So, but these are only common. Field temperature will be a bulk temperature, average of bulk temperature, and wall temperature. This is called as a film temperature. And flow over flat plate. What will be the film temperature? So it will be a average of this thing actually. Okay. So this is what the you can say film property on bulk property and how they are defined commonly. So sometimes just the wall temperature is used as a film property, film temperature. TW equals to film temperature, CW equals to film concentration. Okay, and sometimes it will be average. But if you see, this is film temperature, this is film concentration, what will be film velocity? So it will be 0 if I assume wall velocity only. So this definition is common. Okay, this film temperature, bulk temperature plus wall temperature divided average of this thing. Average of this thing will be film temperature. Okay, so with this brief, you can say introduction for starting this engineering correlation, we'll stop this today's class, and maybe in tomorrow's class we'll discuss flow or flat plate, how to get the engineering correlation. And if you have anything to add in this discussion of this engineering correlation, we can discuss for a minute, or that's all I want to discuss. This is just a starting of engineering correlation. In next class, we will discuss how to get the engineering correlation, how these engineering correlations are obtained.